Hello students, I am Professor Ambika Devi, Assistant Professor of Physics, Government First Grade College, Bidar. Today's video is related to Session 30 of BSc 5th Sem Solid State Physics course, which is prescribed in the colleges affiliated to Karnataka State, Gulbarga University, Kalburgi. Let us now begin with the session 30 of BSc 5th Sem Solid State Physics course, and this session is related to quantum theory of paramagnetism. Students, see in this slide, we will discuss occurrence of electronic paramagnetism. Okay, means where it occurs, where paramagnetism occurs. Actually, paramagnetism occurs in atoms, molecules, and lattice defects with odd number of electrons. And also it also occurs in free atoms and ions with partly filled with inner shell. Okay, and it occurs in few compounds with even number of electrons, and it also occurs in metals also. Okay, so according to quantum theory, the permanent magnetic moment of a given atom or ion is not freely rotating, but it is restricted to a finite set of orientations, and it is relative to the applied field. Then the magnetic moment of an atom or ion in a free space is given by mu equal to minus g mu b j. Call this as equation number 1. Here j be the total angular momentum. All of us we know that total angular momentum is equal to sum of the orbital angular momentum and spin angular momentum. Okay, so here the ratio of magnitude of mu to the to that of j is called gyromagnetic ratio, that is represented by gamma, or magnetogyric ratio. See here, mu b is the Bohr magneton, and this Bohr magneton is defined as it is the ratio of EH cross divided by 2m. For a free atom, the G factor, this landed G factor is given by G is equal to 1 plus J into J plus 1 plus S into S plus 1 plus L into L plus 1. It is the sum of total angular momentum, orbital angular momentum, and spin angular momentum divided by 2J into J plus 1. Here G is the Landis G factor. So here this G is here G value is taken as 2, and here energy levels of the system in a magnetic field are also given by minus mu b, and this minus mu b is also expressed as mjg mu b. Okay, here mj be the azimuthal quantum number. Okay, here this one j is the azimuthal quantum number. See here in this figure, thus the energy difference exists between spin magnetic dipole moments which are parallel and anti-parallel to the field. The magnitude of the energy difference is 2 mu b. This is this energy splitting is shown in this figure. Okay. So let us suppose that in unit volume of the paramagnetic material there is a total total number of atoms are represented by capital N. The spin moment of N1 atoms are parallel to that field. Okay, spin momentum is here, two types of spin momentums are there, N1 and N2. N1 atoms are parallel to the field and N2 spin moments are anti-parallel to the field. Okay, if a system has only two levels, the equilibrium populations are, here it is represented by N1 by N is equal to this expression and N2 by N is equal to this expression. Here N be the total number of atoms, N1 be the spin moments of the atoms which are parallel to the field, and N2 be the spin moments of the atoms which are anti-parallel to the field. Then here N1 and N2. N1 and N2 are the populations of the lower and upper levels, and total N is given by it is the algebraic sum of N1 plus N2. Here N1 plus N2 is the total number of atoms. The fractional populations are plotted in this figure. Okay, see here the projection of the magnetic movement of the upper state along the field direction is represented by mu. If the magnetic moments are aligned along the field direction, then it is represented by minus mu, and the lower states are represented by mu. Then the resultant magnetization for an atoms per unit volume is given by M equal to N1 minus N2 into mu. But here M is also given as N mu tan Hx. Here X is given by X is equal to mu B divided by KBT. Then this mu is expressed as, M is expressed as N mu. Here so for if angle is less than 1, then tan theta is equal to theta. So here tan Hx is equal to X. Then here in place of X, we are substituting mu B divided by KBT. Then the expression for M becomes N mu B divided by KBT. In a magnetic field, an atom with angular momentum quantum number J has 2J plus 1 equally spaced energy levels. Then the magnetization is given by M is equal to Ng J mu B into Bj of X. Here X is equal to Gj mu B B divided by KBT. This is, by using this equation, X is equal to, X becomes Gj mu B B divided by KBT. This equation M is equal to this expression. M expression is called Curie-Brillouin law. Okay, then this Bj of X is called Brillouin function, which is defined by this expression. Okay, then next, see this figure, students. This figure shows the plot of magnetic momentum versus B by T. Magnetic moment versus B by T for spherical samples of potassium chromium alum, ferric ammonium alum, and gadolinium sulfate octahydrate. Here, if here X is considered as very much less than 1, so here we have tan Hx is equal to, cot H value becomes 1 by X plus X by 3 plus Q by 45 and so on. Okay, this figure shows the graph of magnetic moment versus B by T for three different materials. Okay, then the susceptibility per unit volume is given by, according to the definition of susceptibility, is the ratio of M by B. Then this equation is modified as psi is equal to N P square 2 mu B divided by 3 kBT into C by T. Here P is called the effective number of Bohr magnetons, and it is defined as P is equal to, using the Landé G factor, G into J plus 1 raised to 1 by 2. This is the Curie law, and here C is called the Curie constant. So students, this is about quantum theory of paramagnetism. So students, I am sure you got the good understanding of the concept of quantum theory of paramagnetism. Okay, thank you.